general relativity step by step. Now last time I set out a couple of equations which were the geodesic equations for polar coordinates, and I'll just write them out again because I got a bit distracted. We've got r double dots equals r theta dot squared, and we have theta dot dot equals minus 2 over r dot theta dot. This is just normal polar coordinates indexed. A point is indexed by its distance from the origin r and angle theta from the x-axis. Okay, so what does the straight line look like in these coordinates? Well, here's my point, and it's going along at some like that, some path like that. What I'm going to do is find this point here, which is the point of closest approach, distance b, and I'm going to say that r and theta, well, theta is easier to do because as time goes by, it's just a constant alpha plus arc tan t over b, I guess, because t being proportional to this distance along here. You may argue, or you may object, that I'm assuming unit speed here, but of course I haven't specified what my unit of time is. And of course r is the square root of b squared plus t squared. So what I want to do is to verify that those equations, it's actually harder than a lot harder than I thought at least, to solve these equations ab initio. You can do it, it's just messy and difficult. So let's start as we are. R equals b squared plus t squared to the 1/2. That means that r dot equals t b squared plus t squared to the minus 1/2, and r double dots equals, let's get this right, b squared plus t squared to the minus 1/2 times t minus t b squared plus t squared to the minus 3 over 2. I'll just neaten that up a bit. So that's 1 over r into 1 minus t, just a minute, t, oh I'm sorry, that's t squared over r squared equals 1 over r squared, that's b squared plus t squared, I guess, b squared plus t squared, and that is b squared plus t squared minus t squared. So it's equal to 1 over r b squared over r squared, which is b squared r to the minus 3, I think. Is that right? R double dots equals b squared over r cubed. That's right. Okay, so that's r dots. Theta equals an arbitrary offset alpha plus arc tan of t over b. So that says that theta dot equals b to minus 1 over 1 plus t squared over b squared, which equals b over b squared plus t squared equals b over r squared. Theta dot dot equals, let's see if I can just write this down, that is going to be b to the minus 1 times 2 t over b squared plus t squared squared, so I've got that right, equals, let's get this right, minus 2bt over r to the 4. Okay, so what's my equations? Well, I've forgotten what my equations are now. Here they are. We're looking to verify that r double dots equals r theta dot squared. I'll do that one first, I guess. Well, the left-hand side equals r double dots, which is this thing here, b squared r to minus 3, b squared r minus 3, and the right-hand side equals r theta dot squared equals r times theta dot, which is b over r squared from here. B over r squared squared equals b squared r minus 3. Check, because they match up. What was the other equation? Here it is. theta dot dot equals minus 2 over r dot theta dot. So theta dot dot equals minus 2 over r dot theta dot. Yeah, so the left hand side equals theta dot dot, which is this formula here, minus 2bt over r4 minus 2bt over r to the 4. The right hand side is equal to minus 2 over r times r dot. What's r dot? R dot is here, which is, that's equal to t over r, I guess, times t over r, that thing there being r dot, times theta dot, which is here, b over r, which is this formula here, b over r squared, equals minus 2tb over r to the 1, 2, 3, 4. Check. Whew, there we go. Let me summarise what we've just been doing. What I've got is a geodesic curve which is indexed just by a point moving in a straight line. I've parametrized it in terms of that closest approach b, and I guess the offset angle alpha. It's moving in a straight line here. And I have shown directly that the motion of that point, which is a geodesic by definition, because it's a straight line, which you can recognize dead easily by looking at it in Cartesian coordinates. But the geodesic equations themselves are these in polar coordinates, and they are satisfied by the straight line movement of this particle here. Which is quite a lot of work to do something that may be obvious. Well, no, that's not the way to think about it. The way to think about it is that these techniques really ought to work for particles moving in polar coordinates in a zero force field. And they do, which is a good start. So I'm going to stop there.